Okay, I'm going to start the recording here. Okay, so we are in now sections. We're continuing section 7.2. Hold on. Let me share and I want to talk about Euler's method today. So let me make the ebook available. Here we go. All right, so you've learned that with a differential equation, you can produce a direction field, also known as a slope field, that will I'm going to say this the right way. The purpose of the direction field is, you have a differential equation and you compute the derivative at different coordinates, and the derivative at each of the coordinates is the slope of a tangent line at that coordinate. You plot all the tangent lines, and solutions to the differential equation have to follow that direction field. You have to obey those tangent lines. So essentially, you can get an idea of qualitatively what solutions look like without knowing how to solve the differential equation. But of course, it is important to be able to come up with values for a solution to a differential equation. And that's what Euler's method is. So the basic idea behind direction fields can be used to find, let me highlight that. The basic idea behind direction fields can be used to find numerical approximations to solutions of differential equations. And what the textbook does is they illustrate the method on an initial value problem. And you've seen this before, this one. We have y prime dy dx equals x plus y with an initial condition that y of 0 equals 1. Okay, that's our standard example in the book. And they comment here that the differential equation, and I like to kind of highlight as I talk, the differential equation tells us that when x equals 0, y prime equals 1. So the solution curve would have to have a slope 1 at the point 0, 1. Right? And what they're doing here is in figure 12, they're drawing the red solution curve to this differential equation. Okay, and again, you don't know how to get that solution explicitly, but just take it as fact that that's what the solution curve looks like. This red solution curve is the solution to the differential equation y prime equals x plus y with the initial condition y of 0 equals 1. Okay, so the solution to that initial value problem, the solution curve, is this red curve. But we know at 0, 1, the derivative equals 1. And so as a first approximation to the solution, we could use the linear approximation, L of x equals x plus 1. So the slope is 1 and the y-intercept is 1. So L of x, a linear approximation, equals x plus 1. How many remember, well, that's fine, that's fine. Okay, so what they've drawn here in figure 12 is they've drawn the solution curve with this linear approximation, L of x. Okay, and you see, for instance, you might want to estimate the solution curve when x is equal to a half. Okay, you might want to, so like for instance, and they're actually talking about that. They're actually talking about that. But if you were to estimate the solution curve when x equals a half, then using the linear approximation, the approximate y value for the solution when x equals a half is going to be a half plus 1, or 1.5. But the thing is, you see, you normally, like this solution curve, we'd like to approximate we'd like to approximate this value of the solution curve for different x values. So the solution curve, which is y equals some function of x, it's going to take on different y values for different x values. We'd like to approximate those y values. And so what we can do is we can use, well, let's take that x equals a half point. Let me highlight this. So we agree that the linear approximation of the solution curve when x equals a half is 1.5. Therefore, y of 0.5 is approximately equal to 1.5. Now what we can do is we can use the 0.5, 1.5 coordinate as the starting point for the next new line segment. When x equals a half, the differential equation, y prime equals x plus y prime of half would equal 0.5 plus 1.5. You see, we're using the previous coordinate from our linear approximation to continue. So at a half, the y prime of 0.5 is equal to 2. And so now we can get another linear approximation for a solution that's greater than 0.5, because y minus y1 equals m times x minus x1. And that's what they're using here to get the next linear approximation. So the next linear approximation would be y equals 2x plus a half. And what they do then is, you see, if we go down to figure 13, now you have an Euler approximation where you've moved out 2 steps. Well, I got to be a little careful here how I phrase it. But what they've done is, from 0 to 0.5, they graph the linear approximation y equals, hold on here, y equals x plus 1. But then between x equals a half and 1, they graph the linear approximation y equals 2x plus 5. Okay, and the point is that you see these line segments are following the solution curve. See that? You notice how this line segments sort of, follow the solution curve? How many are noticing that? Kind of interesting. Maybe give a few thumbs up if you're noticing that in the figure 13. Okay, is anybody? Well, first, are there any questions? Are there any questions? Dan?
Nothing, never mind.
You're good? Okay. So what you're doing, you see, is you used the original point 0,1 to draw a tangent line. And the tangent line went out to 0.5, 1.5. And then you're computing the derivative, which you can do because you know the differential equation. You're computing the derivative when x is a half and y is 1.5. And then you're going to draw, based on that, since you'll have the slope for x equals a half and y equals 1.5, you'll have the slope is 2, and you have the coordinate 0.5 and 1.5 as a point on the next line segment. And so you can get the equation of the next line segment and draw the next line segment. And you can continue with this process. You can continue, see, and you can adjust your step size too. There in figure 13, we used a step size of a half, but we can adjust the step size to 0.25. And so, like for step size of a half, from x, when x goes from 0 to 1, how many line segments are there? In figure 13, how many line segments were there when you had a step size of a half? You're using the line segments to approximate the solution curve. So if x is between, let's say we want to approximate the solution curve when x is between 0 and 1. Okay, so in figure 13, we use the step size of a half. How many line segments does that give us? Okay, that's right, Kahindi. That gives us 2 line segments. 2 line segments. But when you go to down to a step size of 0.25, as in figure 14, how many line segments are there? Okay, that's right, Candy, there are 4. So let me ask you, which set of line segments approximates the red solution curve better? Figure 13 or figure 14? Indeed, it is figure 14. Thank you, Rodrigo, Tina, and Kahindi. All right, very good. And so you see the approximation, the approximating the solution curve gets better if you decrease your step size. But notice, as the original point that we worked from was 0, 1. What happens to these approximating line segments to the solution curve as you move out from your initial value 0, 1? Do the line segment approximations get better or worse as you move out? What do you think? Okay, so I'm hearing better. Well, let's focus on figure 14. So the first line segment goes from 0 to 0.25. That approximates the solution curve. The second line segment goes from 0.25 to 0.5. That second line segment goes from 0.25 to 0.5, and that's worse, right? That line segment. I mean, and then the third line segment is getting even worse. And the fourth line segment from 0.75 to 1. It's following the solution curve, but it's getting worse. So you see, we can control. Now people are understanding. Yeah, as we step out along the direction field or the slope field, the Euler approximation will get worse as you move away from your initial value. But the thing is, with computer power these days, we can control that. If we have a very small step size, we can approximate that solution curve over a wide, like a large interval over x. Okay, we can with a smaller step size, we can approximate it better and better, the solution curve. So, like for instance, let me see here. I have a nice picture here. See this here in figure 16? Okay, so here they have some different Euler approximations to a solution curve where they use different step sizes. The green, the Euler approximation with the 2 green line segments there is for step size a half. The Euler approximation with the purple line segments is with step size 0.25. But if you decrease the step sizes, you can see like the yellow and the blue Euler approximations are pretty close to the solution curve from 0 to 1. So even though we don't know the explicit solution to this differential equation, we can still find approximate solutions to the differential equation. And this is what Euler's method is about. And we stepped out twice along the slope field using the example that they give in the book. And there's a general formula. So it's an iterative procedure. So for instance, what we do is we denote the derivative y prime. We denote it by capital F of x naught, y naught. Now, capital F doesn't mean antiderivative or anything like. It just means that your differential equation, y prime equals the right-hand side. The right-hand side is going to be a function of x and y. And so the first iteration the y1 is going to equal y naught plus h. H is your step size, okay, times the slope, or the derivative of f at x naught y naught. Okay, and then the second Euler method approximation y sub 2 will be dependent on the previous values. It'll equal y1, which you got previously, plus h times the derivative evaluated at x1, y1. And we can keep going and going and going. And in general, this is the iterative procedure for Euler's method. The approximation y sub n equals the previous approximation y sub n minus 1 plus h times the derivative evaluated at x sub n minus 1, y sub n minus 1. Okay, and this is what called Euler's method, and they box it here. Okay, and it was created by Leonhard Euler, who lived from 1707 to 1783, and he was the leading mathematician of the mid 18th century. And they have a footnote in your textbook about him, and a lot of interesting things. He had 13 children. That's a lot of children, but he still did his math. Hold on, I heard a chat thing there. Yeah, Tina, yeah. Well, and let me see. Let me just see if there's any information. I mean, sometimes, let me just see if they have any information here. Yeah, there it is. I'm gonna read that for a minute. It's worth doing. So let's see. Leonhard Euler was born in Switzerland, but spent most of his career at the Academies of Science supported by Catherine the Great in St. Petersburg and Frederick the Great in Berlin. Okay, so they didn't have community colleges back then. You maybe have to have a sponsor to pay for your way through school. Of course, you're paying your way through school, but you know what I mean. In the very nice 21st century, a lot of students are able to go to college. Back then, much harder. But says here, let me see, a lot of interesting things. Says his treatise on calculus and most other mathematical subjects became the standard for math instruction. Okay, and I mean, there are like volumes of his work. There are well, actually, it says here the collected works of Euler, right here, are about 100 volumes. What do you think of that? That's pretty cool. How many think? How many are kind of think that's pretty cool, what you just read there? Well, I mean, I hope maybe one or two people might think it's pretty cool. So I need a few thumbs up to make my recording look good, right? All right. Adriana says it's, yeah, I hear you, Adriana, that he'd have 13 kids. But I doubt very much I mean, I don't know, but he probably had a lot of help, So, all right. So Adriana thinks Euler's interesting. Tina says, well, Tina says she wished she could swap his brain for his. Hey, you're all, learning calculus 2 here, and who knows what the future's in store for you, Yeah. Yeah, so Snega, you all, who knows? Who knows? I mean, you can discover new things. But on that note let me go back to the Euler's method. So this is the general Euler's method. And what I want to do, I think it'd be best to use an example to demonstrate this. So let me go ahead and share an example here. Let me see here. This is not, hold on. Just give me a moment here. I got to find the right file here. Give me one moment. There we go. I had uploaded the wrong file. I got to get this, I have to have my files listed in alphabetical order, or I mean, like by date. Sometimes it doesn't do that naturally in Explorer. So I know there's a setting. And, all right, so let me, okay. All right, take a moment to copy this example down. Okay, take a moment, and then we'll discuss this. Okay, all right, so now let's look at this problem. So we want to use the Euler's method with step size 1/2 to estimate y of 3. When x is 3, what's the y value? That's what y of 3 means. We want to estimate this value for the solution of this initial value problem. And now again, when you take differential equations, which is Math 282, you'll learn how to solve this type of differential equation. It's a linear differential equation, a non-homogeneous linear differential equation. But you'll learn how to explicitly solve it in 282. But for now, we have to, if we want to estimate what the value of the solution is when x equals 3, we're going to have to use Euler's method. So let's go ahead and let me show you how this works. So the interval, well, okay, so where I'm starting at x equals 1, right? This is because remember, they tell us that y of 1 equals 0. So that means then that my initial x value is 1. But we're going to use a step size of 1/2. Now, practically speaking, you're not, step size of 1/2 would normally not give you a good approximation. But since we're working this out by hand so you can learn the technique, we're going to have, manageable step sizes. So I have to get the approximation for my solution when x equals 3. So that means if I'm using step size of 1/2, starting at 1, I have to do 1 iteration, 2 iterations, 3 iterations, and finally 4 iterations to get my approximation. All right. And here's my initial x and initial y. And now, when x equals 1.5, I want to find I want to get the approximation of the solution y1 when x is 1.5. So by Euler's method, then y1 is going to equal y naught plus h times f of x naught y naught. And remember, f of xy is y minus 2x. So y naught is 0. Step size h is 1/2. And then I put in 0 minus 2 times 1, which is -2. See, that's the value of the derivative at the point 1, 0. And so y1 will equal -1. Now let's go out, let's move out to x2 equals 2. And you see what I did in the beginning, I made a little chart. I had 1 to 3 with a step size of 1/2, and then that allows me to easily just keep things straight in the Euler's method. There's x1, x1's 1.5, okay, and so y2 is equal to the approximate value for y2 is based on the previous information. It equals y1 plus h times the derivative evaluated at x1, y1. Okay, and when you work that out, you're going to get -3. So I'd like to pause for a minute and just see if you have any questions so far on this. Okay, one moment. All right. Let me see. Okay, people are good. Not Nell, question?
Yeah, I have a question. So I understand you use the values from the previous. So like for my question was like for when we said x2, I understand x2 equals 2 and then y2. When we did the y2 part, we said
Okay.
the formula is y1 plus hf and then y1 and I mean x1 and y1. How come we didn't use the 1.5 from the previous where we said y1 equals 1.5?
Well, x1 was equal to 1.5.
Yeah, that's what I meant. Like how
Oh,
come?
we did. Here it is. Very good question. Here it is.
No, I meant like in the oh yeah.
So my derivative is y prime equals y minus 2x. That's my derivative. So I'm using that. That's also defined as the big F function. So big F of x1, y1 would equal -1 minus 2 times 1.5. Because x1 is -1. No, I'm sorry. Hold on. Y1 was -1 and x1 was 1.5. And then, by the way, you see it here for x3. x3 is 2.5, and you can evaluate y3. And you can then do the same for x4 equals 3. You can evaluate y4. You're just iterating.
Okay. Like okay. And okay. One more question.
Sure.
So like for the first one, we said y1 equals -1. Correct?
Well, because I computed y1
Yes. Yeah. Yeah. I
equals
understand that.
-1, right?
Yeah. And how come we used -2 on for when we were finding out y2? I understand the -1 came from y1, but how come we used?
Oh, this -2 here.
Yes.
Okay, I see. This -2 here is this -2. So that in the parentheses, you see each iteration, there's something after the 0.5, there's something in parentheses. What's in parentheses is the derivative, y minus 2x, evaluated at the different points. There's always a -2 there. It's part of the formula. It's part of the formula. You see, y prime equals f of xy. The big F of xy here is defined as y prime. And so when you see big F, these big F functions evaluated at the different coordinates, it just means compute the derivative for those different coordinates.
Okay. Like I was also confused on how you got the derivative and the h.
So it's given to you. You have to be given the derivative.
I mean, like where you said f and then x comma y. Like I don't understand.
Well, that's in Euler's method. The f of x comma y is defined as your derivative.
Oh, is it so? Always that's going to be our derivative for.
Correct. That's right.
Okay. And then how come we put like an h?
Well, it's part of Euler. It's part of the Euler's formula. Hold on one moment. One moment, and I'll go back to the thing. Hold on, everybody. I can see. There's the Euler's method right there.
Okay.
That's where I'm getting. That's how I'm doing my iterations. Okay, so like when n is 1 in this formula, you'll get y1 equals y0 plus h times f of x0, y0. When n is 2 in this formula, you'll get y2 equals y1 plus h times f of x1, y1. That's all you're doing. All right?
Okay.
And by the way, y prime equals f of xy. So this Euler's method formula, you'll probably need, I mean, I think when you work on your homework, you'll be referring to it. It's in section 7.2, just before example 3.
Okay.
All right, great. And the book has a nice example, but I'm also trying to work out, I want to work out my little example too. So now, let me see here. Okay, so what I'm going to do now, is I have my, I want to say this the right way. So I have these coordinates. Okay, I have like I start out at 0, 0. And then I get, no, I'm sorry, 1, 0. And then I get 1.5, negative 1 from the first iteration. When x is 1.5, y 1 equals negative 1. Okay, what would the next coordinate be for my approximate solution? What's the next coordinate?
Um, 2, negative 3.
That's right, Tyreek. 2, negative 3. Okay, what's the next coordinate? That's right, Tina, 2.5. And negative 6.5. And then the final coordinate is going to be, and I think Rodrigo had said it, 3, negative 12.25. So these, for different x values, for x equals 1.52, 2.5, and 3, you're getting these different y values, which are approximations to the solution. But of course, the ultimate answer we're interested in is when x equals 3, what is y equal to? What's the approximation? And the answer is going to be negative 12.25. In other words, we can say, let me ask you this. Can we say this? Can we say that y of 3 equals negative 12.25? Is that a true statement? Y of 3 equals negative 12.25? Ah, okay, good, Michael. And I think Tina agrees. It should be y of 3 is about negative 12.25. That's right, Colum. It's an approximation. And about, it might be, the about may not be that good. But we're saying we think y of 3 is approximately equal to negative 12.25. That's the answer to that's our estimate. That's our estimate. Now, I have here, by Euler's method, y of 3 is approximately negative 12.25. And I note that in differential equations, you will learn that the solution to this differential equation, and to that differential equation, y prime equals y minus 2x, you'll learn that the solution is actually y equals negative 4 over e times e to the x plus 2x plus 2. Okay, you'll learn that. Okay, if you take differential equations. And incidentally, I am scheduled to teach that next semester. I believe open enrollment starts on Monday. Is that right? I believe, where you can register for classes for the spring. Has anybody gotten any like notification on that email or anything? Has the college sent you any info on that? All right, all right. Well, you probably will get something very soon. So what I've done here is on this XY axis, I've plotted the those coordinates. Okay, and actually, what I'm like. The coordinates that I'm highlighting in red are the coordinates based on the Euler's approximation. Okay, that's what that is. And the exact solution, if you were to graph that, the solution would look like that. Get a little. Okay, so that is going to be y of x. And the point is, so let's see here, I want to say this the right way. When x is 3, here's the value of y. The value of y is maybe like, well, let me see. If we were to, I can actually compute that by plugging 3 into the exact solution. One moment. Just give me a moment here. You're welcome to plug 3 in the exact solution as well. To see here. Oh wait, hold on. Hold on. I'm gonna get it. Yeah. The actual value when x is 3. Let me just put it maybe in blue here. When x is 3, y is about equal to negative 21.6. This here is the exact value. And the way I got that exact value was I plugged in x equals 3 in my solution. So how did the approximation do? Okay, so the exact value of the solution when x equals 3 is negative 21.6. Michael says the approximation didn't do well. Well, what did our approximation tell us, Michael? What was the approximation when that Euler's method gave when x is equal to 3? That's right, Rodrigo, and I'm sure Michael knows too, negative 12.25. So you see, approximation didn't work too well. How could we make the approximation better with Euler's method? How can we make our approximation better? That's right, everybody. Michael, Tina, Rodrigo, more steps. Smaller, that means a smaller step size. That's right, Cologne. So this is Euler's method, and it's actually extremely helpful for if you can't get a solution to a differential equation, if you cannot get an explicit solution, you can use it by just adjusting your step size so it's very small, which we can do with computing power these days. You can get an approximate solution that's excellent, basically indistinguishable from the true solution. And again, you'll see that in differential equations. This is what Euler's method is. Are there any questions at all before we move on? Okay, I'll stop the recording.